Alright, welcome. The topic of today is recursion. This is one of the hardest topics in this class, so I put some skulls as well as some warning signs. So definitely pay a little bit of extra attention to these slides, but I do promise it's very satisfying once you get it. This idea of recursion, you've never seen anything like it before probably, but it's very, very cool. Alright, and a lot of people like to make memes about it because we all like struggle with it together. So here are some silly picture examples of recursion. What recursion is you're trying to find something, you're trying to find a smaller version of your same problem inside of itself. I know that probably doesn't make a lot of sense right now, but here's like a silly pictorial example of recursion. This is like a tea or a coffee tin from a long time ago, but like on the coffee tin has a woman holding a cup of tea or coffee with a copy of the tin on it itself, and she's holding it, and it zooms in forever, right? So that's kind of cool. That's recursion. These Russian stacking dolls are also like recursion, aren't they? You got like the biggest one, and then inside of that, oops, what have I done? Inside of that, you've got this one, a smaller version of itself inside of itself. And this is probably the best picture to talk about recursion because there is a smallest doll, and that will be very, very important when we get to solving problems recursively. And then also, like, a lot of fractals are recursive. You see, like, here's the outer thing, kind of looks like a Triforce from Zelda. You see that you've got copies, you got 3 copies of that outer triangle inside of itself. And you can just keep on zooming. Do you see it? That's recursion in a nutshell. So, yeah, let's talk about it. It is weird, but we're all in it together. All right, so plenty of memes about it. I think you'll have fun looking up them and sharing them on our Discord. So yeah, what recursion is, the best way to explain it, in addition to what I've shown you in pictures, is like it's the opposite of it's the opposite of this thing called iteration, which we've been using. So we've used iteration so far to do loops. That's how we solve repetitive problems. Recursion is a way of looping without loops, if that makes sense. All right, so if I say iteration or a problem is solved iteratively, that means we've been using loops. So like this. Oh, let me fix my pens real quick. It's like a for loop. That is an example of iteration. And so this will repeat its body 42 times. But recursion is a way of looping without a for loop, without a while loop. It's interesting, all right? Looping without loops. So let's figure this out together, because how is that even possible, you might be wondering. Well, I will show you. So again, just if you want to spell it out, recursion is when you have a problem and you're solving it using smaller versions of that same exact problem, which is weird to think about, all right? And eventually you'll make your way down to the smallest problem, and you'll start building up the answer. You'll build up the bigger answer using the smaller versions of it that you're finding, okay? A common first example for recursion is factorial. The problem is solving for the factorial of a number. I claim that that is a recursive problem. First of all, let's just make sure we're all on the same page and we remember what a factorial is. Factorial is that exclamation point from math. It's like 5 factorial, that's equal to 5 times 4 times 3 times 2 times 1. Whatever that number is, yeah? So let's break this problem down recursively now on this slide. I have a question for you. So, okay, I claim that factorial in general is a recursive problem, which means you should be able to find a smaller version of the factorial problem inside of your original one. So let's say we start with 5 factorial. Can you break it down like this? Can you find a smaller factorial inside of 5 factorial? Here's 5 factorial again. 5 times 4 times 3 times 2 times 1. Do you see it? Pause the video until you do. There's a couple, right? So there's 4 factorial sitting right there. And then there's every other one too. There's 3 factorial, there's 2 factorial, there's 1 factorial. Technically there's also 0 factorial. That's defined to be 1, so like that's in there too, if you want to think of it that way. But yeah, in general, when you're solving a problem recursively, you're just looking for the next smaller one. So 4 factorial is the one to notice here, okay? But all the rest of them are in there too. And that's kind of interesting. So we can define 5 factorial then to be the extra work, 5, times the smaller problem's answer, 4 factorial. Does that make sense to you? We're defining 5 factorial in terms of a smaller version of itself, and that checks out. That is correct math. That's going to lead to a program that loops without loops, which is crazy, all right? So yeah, what we noticed was that, okay, 5 factorial is equal to 5 times 4 factorial, and that generalizes. All right, so we had 5 factorial. That was equal to 5 times 4 factorial. We noticed that. And what's 4 factorial? That's equal to 4 times 3 times 2 times 1, which is equal to 4 times 3 factorial. Do you see a pattern emerging here? Because what? Okay, 4 factorial is equal to 4 times 3 factorial. 5 factorial is equal to 5 times 4 factorial. It's all in there. So in general then, what do we get out of this? If you want to ask me for n factorial, for any n, what's the answer? Just following this pattern, right? Well, your factorial, n factorial is equal to n times n minus 1 factorial. Do you see that? That is the general solution, recursively, using a smaller version of the problem. Isn't that cool? So yeah, in general, that's true, and that is called the recursive case of your answer. That's called the recursive case. So I'll put a box around that. That's important. So that's the recursive case of the factorial problem. All right, recursive case. And then you can kind of use it all day long to get your answers, more or less. Like 4 factorial, like it breaks down in the same way. You do need to find a place to stop, though, because you don't want to keep on unwinding forever. You'll never get anywhere, right? So you're going to keep using those smaller problems. They're called sub-problems to solve your bigger problem, right? But eventually you need to stop so that like you don't just go on multiplying forever until the end of time. You need a final answer eventually. You need to get one. So we need to pair our recursive case with a stopping condition. And the way to find your stopping condition is like to keep on unwinding this according to the recursive case rule and like see when things stop making sense. When does the problem get so small that like all bets are off, nothing makes sense anymore, or like the problem is so small that I know the answer immediately, I don't have to do any extra work. So let's try that. So 3 factorial, if we keep following this this rule, 3 factorial is equal to 3 times 2 factorial, which is correct. That checks out. So okay, let's keep going. 2 factorial, according to our recursive rule, is equal to 2 times 1 factorial, which still checks out. That is mathematically correct. No problems there. 1 factorial, according to our rule, looks a little weird. It's 1 times 0 factorial. But 0 factorial is defined in math. It is defined to be 1, so this is still a correct answer. And then, okay, 0 factorial, according to our rule, is equal to 0 times negative 1 factorial. And this is where everything stops making sense. So if you multiply 0 by all your work that you're doing, you've just made the answer 0. So first of all, that's bad. And then also factorial is not defined for negative numbers. So this is not correct to even do any of this right here. So everything stops making sense here for sure. And then we probably haven't used 0 factorial a lot. So let's stop here. If anybody asks us for 1 factorial, the answer is 1, right? That's a nice stopping point. I think we can agree on that. It's like I don't have to do any extra work. I know, just like looking at that, the answer is 1. A nice stopping point. I hope that makes sense. And that becomes what's called a base case. That's our stopping condition. There's at least 1 always. So like if you ever see 1 factorial, just like tell the person who's asking the answer is 1. I'm done. Call it a day, okay? That's called the base case of your recursive solution. That's when it gets so small that you're done. And then you can unwind. Okay? So yeah, with these 2 rules together, we have the full solution. We can eventually work our way, starting from 5 factorial, unwinding the rules down to here, get the final answer of 1, and then you can do the math, work it back up, if that makes sense. All right, try that. I think that would enlighten you. So yeah, in general, what we just learned is the following. We've got the factorial problem can be solved recursively with the following base case. Just like 1 factorial is 1. And then this recursive case. In general, if it's not 1, n factorial, something bigger, the answer is n times n minus 1 factorial. Throw off the problem to a smaller version of yourself. Okay? That's the goal. And let's kind of watch it work. So if you immediately ask, like, I want to know 5 factorial, you can use these 2 rules to get the answer. Do you see? So it's not 1 factorial, so the base case doesn't apply to 5 yet. So we got to use this one. How do you break it down? Well, that's going to be 5 times 4 factorial, and then we just keep on unwinding. This is still not 1, so that's 4 times 3 factorial, 3 times 2 factorial, 2 times 1 factorial. And then 1 factorial, we have the answer, right? You ask me for that. The answer is finally 1. That's my base case, and like I can give that back as the answer for 1 factorial. It's like, okay, yeah, 2 times 1. that answer is 2. So this gives back 1. My answer is 2. You see how that was the correct 2 factorial? It's like, all right, 2 factorial is 2. Use that to make 3 factorial. Give back 6. That's the correct 3 factorial. Multiply it by 4 to make 24. That's the correct 4 factorial. You see it working? And then like, all right, 4 factorial is 24. Use that, multiply by 5 to make 5 factorial. There's your answer. It's 120. Does that make sense? That's the secret. That is the secret, and I think that is all that I wanted to say. So do you see how, like, if you ask for it, you can break it down and then build the answer up once you get to the base case? And that's what we're going to do inside of the computer. That's what code will eventually do for us. So yeah, you do have to be careful. These rules don't always apply. So like, we have not defined 0 factorial. It would like make an infinite loop kind of in math. That's not good. Though that one does exist, but also like -1 factorial, you might end up using this rule accidentally. Like, you want to make sure to enforce the fact that that can't ever happen with like an if statement in your code, because it would unwind forever, right? It would never make its way down to 1 because it's already less than 1. So that's just stuff to worry about. But in general, we just need to turn this into code now. And how do we do that without a loop? What in the world? So I guess we're solving a problem, right? And usually we write functions to solve problems, like give me a factorial function. And if it's recursive, if it's defined in terms of ourselves, how do we handle that? So like, we have a fact function that takes the number n that we want to take the factorial of. The secret is, what we're going to be doing with recursion is that to use a smaller version of ourselves to call, or to like ask for the smaller factorial, but we're the ones writing the factorial function, it ends up happening that we call ourselves. All right, a recursive function is a function that calls itself on a smaller version of the problem. Okay, that makes sense. So this fact of n is going to call, in the recursive case, fact of n minus 1. We get to call ourselves, hand off the problem to a smaller version of ourselves in the hope that we will eventually make it to the base case. Isn't that neat? So yeah, this is the answer for the recursive case. Return n times n minus 1 factorial, but we're doing that. That's our problem. So just call ourselves. It'll give back the answer eventually, once it makes its way. Like, it will do this in code, essentially. Make its way down, work its way back up, and I'll show that to you. Isn't that cool? And then the base case, like, if you notice that it's just 1 factorial, it just immediately the answer is 1. Return it. Those are your 2 cases, and we can implement that. All right, so here, let me show that to you, and it's just kind of magical the first time you see it, but it will work. So all right, let's ask for the factorial of 5. I'll say fact for factorial. And yeah, it's int fact takes a number n that we want the factorial of, and its job is to return n factorial. So we're coding this, we just have to notice which case we're in. We're either in the base case or the recursive case. We're in the base case if n is 1. Somebody asked me for 1 factorial. That's the base case, right? 1 factorial is equal to 1. Otherwise, let's just assume the user didn't call us with a negative number or 0, and we're in the recursive case. That is n factorial is equal to n times n minus 1 factorial. Okay, so yeah, in the base case, just return 1, that's your answer. For 1 factorial in the recursive case, return your n times whatever n minus 1 factorial is, but we're the ones computing that. We can hand it off to a smaller version of ourselves. And that is allowable, because eventually it will make its way down to the base case. It's making progress, if that makes sense to you. Okay, it is weird to think about, but that'll do it. Here. $120, that's the answer. Isn't that neat? And it will always work. Factorial of 4 correctly will be, what was it, 24? It's always going to work. Crazy. It's looping without loops. That's wild. So we can also, I think you can imagine, it's very easy to use like a for loop to do factorial as well. We can make an iterative version then that does the same thing. And maybe that way makes a lot more sense too. That's fine. An iterative version of the factorial problem would be just like building up a product, right? Looping. So int product equals 1. And if somebody asks for like the factorial of 5, just like start at 5, go down to 1, I minus minus, to start off like and multiply into product. Product multiply equals I. So like it'll multiply 5, then 4, then 3, then 2, then 1, if we ask for the factorial of 5 based on this loop. And then just return your product. So like that's another way to do it, that's fine. You'll get the same answer. But recursively, it does the same thing without a loop. That's a little interesting, all right? It's useful. So yeah, you do have options for factorial. It's an easy problem to solve with a loop, but there are problems that can only be solved recursively, and I'll show you some of those eventually, okay? So yeah, we have options now at least, but sometimes it really is easier to think about the recursive solution, or there is no iterative solution. There is no way to do it with normal loops, okay? So this is why we're learning it. All right, so let's draw what's happening on the stack when this function gets called, because that's the magic. That's the looping without loops. It's a bunch of calls to ourselves sitting on the stack at once. So here, yeah, the runtime stack looks very, very cool. So let's look at fact of 5. We're down here in main, and we're calling fact of 5. We jump up here. Let's see what happens. So main calls fact of 5. Fact of 5. I'll draw it like this, even though that's lazy. Fact really has a variable n that's what's holding the parameter 5. Boop. The argument. So that's really what it looks like. But I'll just say fact of 5 to make it a little bit shorter and easier. But yeah, let's go from there. So fact of 5 is getting called. We're asking for the factorial of 5. It needs to return that so we can see out the answer. So it's up here. It's like, all right, 5 is not 1, so here I'm in the recursive case. I need to return my 5, my n, times the factorial of 4. And it does not know that answer yet. So it has to go off. It's not ready to give back an answer from the final return because it needs to multiply its n by something it doesn't know yet. It needs to go off and call this function, get an answer back for fact of 4. You see that? So fact of 5 is going to wait. It's going to wait on this line. Like, I don't have my final answer. I can't do the multiplication yet until I have this. Go compute that. It'll go ask a smaller version of itself. So fact of 5 will call fact of 4. Does that make sense? And again, that's really a variable 4. Like these are two calls to the same function. They have different versions of their n variable. Okay, that's fact of 4. N is 4 up here. It's a different call to the function. Okay, and then fact of 4 is going to get to the same spot. It's like, all right, 4 is not 1, so I need to multiply my 4 times fact of 3, and that's what I return. I don't know what fact of 3 is yet. I'm not ready to do the multiplication. I need to go off and compute fact of 3. So fact of 4 is going to call fact of 3. You see it? Its n is 3 now. There's 3 calls to the function running right now. The bottom 2 are waiting on this line. They're not ready, okay? They're all running at once. Fact of 3 is like in charge right now, but fact of 4 and 5, they're waiting. They're waiting on the person above them. They need the smaller answer first, okay? So I think you can imagine what's going to happen now. So fact of 3, again, it's the recursive case. It goes off and it calls fact of 2. Its n is 2. So all four calls to the same function right here. So it needs to multiply its 3 by fact of 2. And then fact of 2, if we're in here, it's like still not 1. So it needs to multiply with its 2 by fact of 1. So it needs to go off and compute, ask for fact of 1. Its n is 1. And that's finally our base case. So finally on this call, like everybody else is waiting. All these guys are waiting on this line for the smaller factorial above them to finish. And now we finally made our way to fact of 1, which is finally 1 is equal to 1. So it returns its answer of 1 back to the person below it on the stack. And it pops itself off. All right? Does that make sense? That's what's happening. And then now we're back in fact of 2, who was just waiting for fact of 1. It finally got the answer. The answer is 1 for fact of 1. So it can take its 2 and multiply its 2 by 1 to compute its final answer that it needs to go off and return to the person below it. Now it's done. Gives control back to fact of 3. Now fact of 3 is on the top. I really should be erasing these, but I just want to draw a slash so that you see what's happening. So now we're back in fact of 3. It was waiting ever so patiently for fact of 2. It just got that answer back. It was 2 for fact of 2. It can multiply its 3 by that now, and it has an answer. So that's 6. Now it's done. Give its answer back to whoever's below it on the stack. That was fact of 4. Waiting even more patiently for fact of 3. It got the 6 back. It can multiply its 4 by that 6 and return 24. Now it's done. Now we're back finally in fact of 5, who was waiting forever on fact of 4. It's finally completed, made its way, and it got back fact 24 for fact of 4. It sees that now. It can multiply its 5 by that to give back its final answer of 120. And now fact of 5 is done. It returned its answer back to main, who was asking for fact of 5, and it just sends that to cout, which can then go and print 120. Does that make sense? So fact of 5 is calling fact of 4, 4 is calling 3, 3 is calling 2, 2 is 1. Fact of 1 is the base case, it's finally done, returns back to whoever's below it. So it makes its way all the way up here, and then it unwinds back down up to the base case, and then it's unwinding using that recursive rule finally, because it has the answers for both sides at that point. I hope that makes a little bit more sense now. That's really what's going on, all right, under the hood. In recursion, that's why it's looping. Like each iteration is a different call to the function, essentially. Okay? So yeah, let me try to do some math for you now. Recursion is a very powerful concept, and I kind of want to prove to you like why this will give you the right answer, why recursion works, why the smaller call will eventually do the right thing for you, all right? Because that still might not be apparent. So in math, let me do some hand-wavy math to you. You'll understand this fully when you take CSCI 26. But all right, let's pretend that the problem we're trying to solve recursively is just generic. Its name is P. We're solving a problem P. Here's what the base case and the recursive case kind of mean in math. It's like the base case is you shouting out to the world that I know how to solve P of 0, the smallest version of this P problem. That's what the base case gives you. Like, I know the answer immediately, ask me for it, I can give it to you. Right? That is what you're claiming with the base case. I know how to solve this very smallest problem. And then the recursive case is kind of like this. It's saying, if you give me, if only I had the answer to a one smaller version of the problem, I could use that with some maybe extra math to build up the bigger answer to my one bigger problem. Does that make sense? That's what the recursive case is looking like always. You give me the size one smaller problem, like P of k. I can use that answer, maybe do some math, to build up for you the next sized problem, P of k plus 1. That's what the recursive case is claiming. Do you see that? Like, you give me this, I will give you that. I'll find a way. That together may not be clear, but if you think about it enough, these two rules together will solve P of n. They mean that I know how to solve P of n for every n bigger than or equal to 0. I'll solve it all the way to infinity because I can run both of these rules when I need to. Okay? So like P of 0, let me show that to you. Like, let's say we want to compute P of 5 or something. Like, you can start with P of 0 because you're shouting out to the world, I know the answer of P of 0. And then now you can just keep using this recursive case rule. It's like, all right, plug in 0 for k. Like, all right, if you give me P of 0, I'll give you P of 1. I have P of 0. Here it is. It'll spit out for you P of 1. Does that make sense? That's what's going to happen. And then now you have P of 1, the answer at your fingertips. You can again run this rule with k equal to 1 now. Like, you give me P of 1, I'll give you P of 2. I've got P of 1. Here you go. Give me P of 2, and it will. It'll build up the next bigger one, and the next bigger one, and the next bigger one, all the way to infinity. Does that make sense to you? So that's what's going to happen. In programming, we usually are calling with the original largest version of the problem, and we're like making our way down to the base case, and then this starts happening though. That's what was going on the stack. Okay, so that's one cool thing. That's why recursion works. It's a little hand wavy, but that's mostly the reason, and we can make that precise in a math class. And one really interesting thing that I just want you to get used to now is, it's kind of, I think of it as like the magic of recursion. When you're computing this, when you're trying to figure out the recursive case rule, you don't even have to think about any smaller versions other than one smaller. You don't have to remember anything else. What you get is you get to assume that your recursive call on the smaller problem worked correctly. You get to assume, it's not obvious, right, that this is going to really give you back the factorial of n minus 1, because like that's a job, that's our own job, like how can we logically conclude that? But you just get to assume, because it's a smaller version of the problem, this will really return back n minus 1 factorial, the mathematical actual answer. You get to assume that it really will work. This call will give you back this real answer. As long as you build up the right answer correctly, it will be correct. Right? You get to assume that the smaller call, that's called the recursive call, by the way. This is the recursive call right here, a call to ourselves on a smaller version. You get to assume this really gives you back the right answer, even though that's not at all obvious. It really will work out by making its way down to the base case and unwinding in this way. All right? You get to assume that it's going to work. As long as you build up the larger answer correctly and your base case is correct, this really will turn into the factorial of n minus 1. That's what I'm trying to say. All right? It'll unwind. It'll work its way up. You get to assume that that happened. you don't have to think about any smaller versions of the problem. You just get to assume that it's going to make its way there, and it will work out. As long as you do everything else, it really will. All right? That you will not fully clearly see until CSCI 26, but that is what you need to think about right now. It's just going to work. All right? You get to assume that the recursive call, that's your smaller problem, really did give you back the smaller answer. All right? It really will. I promise. If you do everything else right, it really will. So yeah, that's all that I want to say about math right now. And then here's another problem for us. Here's a question for you. So let's say here's another problem. It's called power computation, right? So power computation, I claim, is also recursive. Like you computing 2.5 to the 5th power. As long as the power is a whole number, this is recursive. All right. So that means that you should be able to find a smaller power computation inside of like 2.5 to the 5th power. Do you see it? 2.5 to the 5th is equal to what? 2.5 times 2.5 times 2.5 all the way to that one. Do you see the smaller power computation? Usually you're looking for the next smaller one. Do you see a one smaller version of the problem? That's the one you want to notice. Yeah, I see a couple of them, right? You just circle 4 of these guys. Like there's 2.5 to the 4th power. Also, there is 2.5 to the 4th power. Do you see that? You can pick it apart anyway. Doesn't matter. But like, here's one version of it. 2.5 to the 4th power. Do you see how it's recursive now? And then, of course, the rest is there too. Like here's 2.5 cubed, sitting right there. Boop. There's 2.5 squared, there's 2.5 to the 1st power, and technically 2.5 to the 0th power is also there. Looks like it's a implicit times 1. Anything to the 0th power is 1. They're all in there secretly, but usually you're looking for the next smaller one. I hope that makes sense. So yeah, let's work our way that way. Maybe just to make it easier, just to make it look more like factorial, let's break it down so that it's like 2.5 times 2.5 to the 4th. So I need to kind of shift over my drawing. Let's use this one as 2.5 to the 4th. Boop, there it is. Cool. So every 2.5 to the 5th power is equal to 2.5 times 2.5 to the 4th power. Do you see how that might generalize? So yeah, let's generalize that. Let's make a function called pow, make our own version that takes anything as the base, but it has to be an integer whole number exponent, right? So we found the smaller power computation, didn't we? So like 2 to the 4th power is equal to 2 times 2 times 2 times 2. That is equal to then, right? You see the 2 cubed sitting right there. Or there, doesn't matter. Either way, 2 cubed is there. So in general, right, what do we got? And then I guess we can keep on trying to play this game. That 2 cubed is equal to that. And you could say, all right, that's 2 times 2 squared. You see how it generalizes to the 4th is that. 2 times 2 cubed. 2 cubed is equal to 2 times 2 squared. So in general, right, what's our recursive case? You ask me for m to the nth power. That's equal to, let me get rid of my underlines. M to the nth power is equal to m times m to the n minus 1th power. You see that? And it generalizes in this one as well. M to the n minus 1th power. Do you see that? So that's the general recursive case. And then we want a base case too, like when are we done? We'll stop our power computation. Like when's a good stopping condition? You can work your way down. Like when is it the problem gets so small that it either stops making sense or like I know the answer. So 2 squared according to our rule is 2 times 2 to the 1st. That still checks out. 2 to the 1st according to our rule is 2 times 2 to the 0th. That still checks out. 2 to the 0th, that's equal to 2 times 2 to the negative 1st power, which is technically correct, but now we have like 0.5s involved. And like, all right, what's 2 to the negative 1st is equal to 2 times 2 to the negative 2, which is technically correct, but like we're not getting anywhere anymore. So I think a good place to stop is like, if anybody sees anything to the 0th power, we are done. The answer is 1, we can go home now, okay? That can be a base case. That's a good base case. All right, so anybody asks you for anything to the 0th power, m to the 0th power, the answer is always 1. All right. You could have stopped it to the 1st power, like anything to the 1st power is that same thing, but like this is more general, right? You can get to this, you can get to a smaller power that way, and I think that's better. So yeah. Excuse me. So yeah, in general, the recursive case, what it's doing is it's trying to find a smaller power computation to work with to build up the bigger answer. And the base case is like, that's your stopping condition. Eventually you're going to get there. All right, so let's do that as a program now. I guess I can steal a lot of this. Let's just start from scratch. Pow.cpp. Here's how I want to use it. It's like, all right, pow 2.5 to the 5th power. Pow of 2 to the 4th power. Pow of 2 to the 5th power. All those fun things. So in general, it's called pow. It takes a double. It can take any base m to any integer power. It's got to be an integer power n. All right, and so its job is to return m to the nth power. And so if m is a double, that means the answer could be a double. So that should be the type of the return value. And then now it's our job to break it down. So again, it's always usually an if else. It's like, if we're in the base case, here's your answer. Otherwise, if we're in the recursive case, here's your answer. So yeah, let's break it down. So if n is equal to 0, that tells us we're in the base case, right? We're taking something to the 0th power. And then otherwise, we're in the recursive case. That's our general solution. M to the nth is equal to m times m to the n minus 1. All right, so let's return those things. So return 1 if we're in the base case, or 1.0 if you want to just be clear that we're using doubles. And then in general, so in the recursive case, we need to return our m times m to the n minus 1th power. M times m to the n minus 1th power. I don't have that, but I can ask myself for it. And I get to assume that this really will give me back the correct mathematical answer of m to the n minus 1th power. As long as I build up everything else correctly, it really will work out. So this really will turn into the right smaller answer. As long as I build it up correctly, it's going to make its way down there. Okay? And that's it. That should do it. Cool, and so I'll take this computer's word for it that that's correct. To the 4th, 2, 4, 8, 16, that is fine. And then to the 5th is times 2, that's 32. That is correct. So I assume this one's right too. Okay? But yeah, it's working. It's doing the right thing. And again, we can draw a stack diagram for like why this one is doing it, why it's getting back 32. So here, let's do pow25, stack diagram time. So main, we were in main, and it was colon. Pow25 is getting ready to print it, right? See how it's like, I don't know the answer, go off and compute it, please. So main will call pow25, so that it has something to give to cout. And then pow25, just remember that these are just variables. This is really like, there's an m variable and an n variable, and they're those. I'm just going to be lazy. So pow25 gets called, and so we're up here, 25. 5 is not 0, so we're in the recursive case. We need to multiply our 2 times 2 to the 4th power, this computation. And we don't know the answer yet, so it needs to go off and compute it. It's going to wait on this line. So pow25 is like, all right, in order to compute my final answer, I need to know the answer of pow24. I will go off and ask for that. Do you see it? So it's making its way up there. And so pow25 is waiting on this line, and then pow24 is in charge right now. It's still not taking anything to the 0th power, so again, it's going to try to multiply its 2 times 2 to the 3rd. It does not know that answer yet, so it needs to go off, compute pow23. 24 is asking for 23. They're all waiting on this line below, okay? And you kind of see the game now. Pow23 is like, all right, I need to multiply my 2 by 2 squared, so I better go off and compute that, otherwise I don't know the answer. I can't do the math yet. So pow23 is going to ask for pow22. Pow22 likewise will ask for pow21. I need to the 1st power to multiply by my 2. And then, yeah, again, right, you've got an m and an n going on. So here's like m, here's n. You've got 2 and 1. We're getting there, right? So, again, to the 1st power computation. n is not 0, so I need to multiply my 2 by POW2 0. All right, I need that answer. Then I'll have something to return. And then I can do my multiplication and the math. So POW2 1 will call POW2 0, where m is set to 2 still, and n is set to 0 finally. And there's our base case. Now n is 0. It will return 1 back to whoever called it. POW2 1 was waiting on this line to multiply its 2 by the answer of POW2 0. It just got the answer back. It was 1. So its final answer is 2. It can return that. Do you see that? All right, I was waiting to multiply my 2 by that answer. I just got the answer back. I'm good. So, sorry, POW2 0 was done. We're in POW2 1. Now it's done. So now we're back in POW2 2. Like, all right, I was waiting to multiply my 2 by 2 to the first. I see my answer. 2 to the first is 2. I will multiply my 2 by that. I have something to return. And that is 4. And that is the correct answer. See how it's working? It's returned. And now we're back in POW2 3. It was waiting on POW2 2. It got the answer back. 4. You can multiply its 2 by that. Now it has a final answer to return. 8. Now it's done. Back in 2.4. It's waiting to multiply its 2 by the 8. It got the 8. So 16 in POW2 5 is finally seeing the answer now from POW2 4. And then it can multiply its 2 by that answer. Now it finally has something to return back to main. 16 times 2, 32. Beautiful. See that? And then main was waiting so patiently. It's like it got the answer back. For POW2 5, it can feed that to cout now. It is happy. And that's why we see 32 on that last line there. All right, I hope that makes sense to you. The stack diagram is very important. You see how it's making its way down to the base case and then unwinding and always correctly giving the right answer back. That is why you get to assume that your smaller call really will give you back, your recursive call really will give you back the smaller answer. It really will get down to the base case and unwind and make it the correct smaller answer. All right, so yeah, I think that is a good one to show you. Let's keep on trucking. I got a few more examples, just a couple more. So again, with great power comes great responsibility. Just like with normal iterative solutions that use like while loops and for loops, you can mess up and loop forever with recursion too, because recursion is another way of looping. So that's a little disgusting, but it is possible. It actually will not continue forever though when you loop recursively, because when you loop recursively and never end, you cannot technically have an infinite loop that lasts forever unless you do something very cool that I will show you eventually. So just in general, you can have an infinite loop with recursion, but because of the way it works, like you're calling yourself, it takes memory to call yourself and use new parameters. You're going to blow up your stack, and it's called a stack overflow. All right, so if you've used this website before, it's called Stack Overflow. It was helping you with C++ probably. You've searched Google for stuff, and it tells you stuff on this website. Now you know why it's called Stack Overflow. It's when your stack gets so large that you run out of memory. If you keep calling yourself a bunch of times, you have to take up space for your parameters and stuff. So it's going to run out of memory. All right, because every stack frame, every function call takes space. It takes the parameters, any local variables, needs to know who you're returning back to. Stuff like that needs to get stored in the stack, and it's going to take up space. So you cannot technically have an infinite loop that lasts forever with recursion, all right? So yeah, that's kind of neat. Because you'll run out of memory, your program will just stop with a runtime error. It's the stack overflow. So yeah, one of the easiest ways to have a stack overflow is to forget your base case. Just pretend like it's always going to work. But not having a base case means that unwinds the recursive case rule until the end of time. Right? So that's something to watch out for. So let me show you some ways to have stack overflows. We'll use the factorial example. So here is, I'll get rid of the iterative version. And I want to show you a couple ways to do it. So I'll call this, this one will be fact1. So its name is now fact1. This is the first way to mess up. So here, issue 1. I'm going to mess this up. Let's forget the base case. It's like, all right, I'll just never check for this. It's like always. Here's the recursive case. Boop. Just always going to return. Always going to try and call fact of n-1. Does that make sense? And we can print that out. We can be like, all right, cout inside fact of 1, or sorry, fact 1 being called with the argument n, whatever that was. Okay, so we can watch it blow up. So yeah, this is forgetting the base case. It's always just going to, like, fact of 5 is 4, multiply fact of 4, go to fact of 3, try fact of 2, try fact of 1, try fact of 0, fact of -1, fact of -2, just keep on going. I encourage you to draw the stack diagram. Whee, there it goes. So it kept going for a while. It's like, all right, it kept on calling itself smaller and smaller. And then eventually it just ran out of memory. It tried to write to memory that, like, was not part of this program anymore. So it turned into a seg fault. That's what your stack overflow will turn into. It will seg fault because it tries to write stack memory that your program does not have access to. It's too much memory. Okay. So yeah, that's one easy problem. Don't forget your base case. And then another easy way is to have a recursive case that does not make progress. So that is also a problem. All right. So for example, it is mathematically correct to say that n factorial is equal to n factorial, but computationally you're not getting anywhere. Does that make sense? Like, just, all right, fact of n, return fact of n. Hand off the same problem to yourself. That would never end. Okay. So here, let's steal this guy again, the correct version, and let me mess it up and call it fact 2 this time. Fact 2, so yeah, the base case is correct. Let's call this issue 2, recursive case does not make progress towards base case. So here, instead of this normal recursive case that's calling fact 2 of n minus 1, getting somewhere, it's making its way down to fact of 1. So this one, I'm just going to say, yeah, the answer is fact 2 of n. Incorrect recursive case. You see it? It's like, all right, you asked me for fact 2 of 5. Oh, the answer is fact 2 of 5. I'll go off and call fact 2 of 5. Fact 2 of 5, we'll call fact 2 of 5, we'll call fact 2 of 5 forever. All right, so let's print that. Inside fact 2 of whatever, and we'll see what's going on. It will never get down to fact of 1, fact 2 of 1, okay? Because it'll just keep calling itself on the same value. Though that is mathematically correct, it is not computationally correct. I hope you see that. So it's never going to make its way down to the base case. That is unfortunate. Oh, and if I ever want that to run, I better comment out the first one. So here, fact 2 of 5 now, commenting out the first one. Now we're running this one, and it's just going to forever call fact 2 of 5. So it keeps calling itself, handing off the same problem to a smaller, same problem to itself. It's not even smaller anymore. All right. So it's just higher up the stack. Fact 2 of 5 is being called 1,000,000 times, and again we get a seg fault because we try to call it another time, save a parameter on the stack, and we don't have room. So a seg fault is what a stack overflow turns into. All right. So yeah, just watch out. Now you know. But that's kind of interesting. You'll at least notice the infinite loop with recursion usually. So there's that. And now I have one last example. It's a fun one. It's called the Fibonacci sequence. So maybe you've heard of it before. It's a famous thing. It's a mathematical sequence that the ratio of values in the sequence as it gets large approximates a fancy mathematical constant called phi, which is like what makes nature beautiful. It's a fun number that you can look up on Wikipedia. Highly encourage you to do so. Honestly, let's just do it now. I would like to show it to you. So Fibonacci sequence. Boop. Look at it. It's like, here's the sequence. It goes like this. It's an infinite sequence, and like it's like what snail shell spirals look like. Like there's the factorial, or sorry, the Fibonacci sequence is in those. It's in like the way that fern leaves are like spread out. It's just really cool and has some cool mathematical properties, and it's found a lot in nature, like apparently on this flower, etc., etc., and a bunch of different places in nature. Like things become the Fibonacci sequence because it's like it's useful. It's useful for natural processes. So yeah, let's make the Fibonacci sequence. All right, it is this though. Here's the sequence. It's 0, then 1, then 1, then 2, then 3, then 5, then 8. And so on and so forth. The next element in the sequence is the sum of the two previous ones. All right, so This is how it works. So it goes 0, then 1, and then the next element of the sequence is you sum up these guys. 0 plus 1 is, add them up, the answer is 1 again. All right. Then the next element in the sequence is 1 plus 1. Take these two guys, add them up, now it's 2, and so on and so forth. So like the next element in the sequence is going to be the 1 plus the 2, that's 3, right? And then you can keep going. Now it's 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, dot, dot, dot. All right, but yeah, usually people agree that 0 starts it. So 0 and 1 start it. And so you can have like indices into your sequence now. It's like this is the 0th number of the Fibonacci sequence. This is the 1th number, 2th number. It's not really the second number, it's really one more than that, right? Index 3 of the sequence, index 4 of the sequence, 5, 6, 7, and it's an infinite sequence. Go on until the end of time. But yeah, let's make a function called fib of something, fib of some n, to calculate the nth Fibonacci number. So like if you ask for fib of 7, it should give back 13. And I claim that that is a recursive case, right? That is a recursive problem, isn't it? Can you break it down? Like where's the smaller Fibonacci sequence number finding in fib of 7? It's supposed to give back 13. Well, fib of 7, what is it equal to? It's equal to fib of 5 plus fib of 6, these two guys. I'll write it backwards. Fib of 6 plus fib of 5. Yeah? There's your recursive calls. They're right there. They're smaller versions of yourself. So yeah, in general, recursive case, that one isn't bad, right? That is going to be, you asked me for fib of n. That's equal to fib of, what? N minus 1 plus fib of n minus 2. There's your smaller calls. You need 2 recursive calls, which makes sense. You need 2 elements of the sequence, but you're calling yourself twice now. Weird. That's supposed to be an n, by the way. Let me fix that. And then that's your recursive case. And then think about what's your base case. Like it works for this guy. Like you have fib of 3 is equal to fib of 1 plus fib of 2, but it does break down once you get over here. It's like fib of 1, according to this rule, is equal to fib of 0 plus fib of negative 1. That doesn't make any sense. And then also for fib of 0. Fib of 0 is equal to fib of negative 1 plus fib of negative 2. Those don't exist. All right, those are question marks. So we need to fix that. So we have to hard code the first 2. After the first 2, like there are 2 before you. But for fib of 0 and for fib of 1, we need 2 base cases to start us off. All right, there are finally 2 base cases. Because for those first 2 numbers, there aren't 2 previous elements. Base cases. Fib of 0, we have to hard code. Like fib of 0 is 0. That is way too small of a 0. Let me fix that. And then fib of 1 we'll define to be 1. So we have 2 base cases. And in the recursive case, we're making 2 recursive calls, 2 calls to a smaller version of ourselves. Isn't that neat? So let's program that. I'll call it fib.cpp for short. And so yeah, we'll be like cout fib of 7. And so it's called fib, takes the number n that we want, and it's supposed to return the nth Fibonacci number, and they're all whole numbers, so int. So just like that, and yeah, let's code it up. Either we're in a base case or the recursive case, hopefully, and it's just if statements, right? We have multiple base cases now, though. If we see 0 or 1 as inputs, if n is 0, we're asked for the 0th Fibonacci number. That means we want 0 to give back. Otherwise, if n is 1, then we're asked for the first 1th Fibonacci number, really the second. The answer is 1. And then otherwise, then we're in the recursive case. Somebody asked us for fib of some other bigger number, hopefully, and fib of n in general is equal to fib of n minus 1 plus fib of n minus 2. And those are my calls. Return fib of n minus 1 plus fib of n minus 2. You get to assume, again, that this really will turn into the n minus 1 Fibonacci number. This really will turn into the n minus 2 Fibonacci number. as long as you build everything up correctly, it really will work out. So that's our recursive case. And so fib of 7, we should see 13, because that's the answer. Let's see it. Boop, boop, 13. All right, so yeah, it's working, and it works for any other number. I do want to stop. This is the last slide I want to go through today, but I want to stop with a very interesting fact. The recursive implementation of Fibonacci, I think you can imagine that you could do it with a loop, with like a for loop or a while loop too. This recursive version, this naive way that we implemented it, is actually really bad. It is horrible. So here, we can make it better. There is a way to make it better and keep it recursive, but let me try to ask for fib of 100. The 100th Fibonacci number. I did fib of 7. It's fine. That one prints 13. Fib of 100, though, if I wait, it's not going to blow up the stack. It's just going to call itself at most 100 times. It's not going to get any bigger than that. It's not going to like blow up the stack. It's not too big. It's going to make its way down to the base case eventually. But just the amount of work that's being done by these two recursive calls, and the fact that it's not like sharing any answers, it has to like redo stuff a whole lot. And we could leave this running for a long time and it would never end. All right, I have a fun thing to tell you right now. Fib of 100, this call, we will all be dead by the time fib of 100 completes right now with this current implementation. It just so happens that to finish this fib of 100 call, if there was a way to keep my computer powered for long enough, the sun will have exploded by the time this finishes. It takes longer. It will take longer for this fib of 100 call to complete than the amount of time that the universe has existed so far. Billions of years. Is that not amazing? That's crazy. This call, for some reason, it will take billions of years to complete. I don't have that amount of time, so I'm going to Control-C, get back to the terminal. But that's a very interesting thing to end on, I think. All right? See if you can kind of figure out why it's being like that. But that's where I want to stop for now. I'll tell you the secret next time. There is a way to make it better, but it will take a future class to get there and keep it recursive. You can, of course, do it with a loop very easily, but it's something to be said there, and we'll get to it soon. All right? So I'll see you in the next one.